Yeah, so this is kind of one of those talks where I fired out the title. It just came to me in a burst of inspiration, followed by perspiration, and quickly whipped up an abstract and sent it off to Monica, and then thought, oh hell, what am I actually going to present? So it goes off on a few tangents and probably spends more time talking about the virtues of Erlang for doing applications on SMP, multi-core environments and so forth. But hopefully there'll be some bits and pieces in there that are of interest to you. A little bit frustrating having to stand here behind the lectern because, you see, I chose this T-shirt to try and distract people from the talk and things like that, but you can't really see it properly, although maybe I'm tall enough. But anyway, so I'm not going to read the title again. You've read the abstract and things like that, and that's why you're here. So my name, Brett Cameron. As was said in the introduction, I've been around for a disturbingly long time now. I started out in the IT industry back in about 1992. I'd finished my PhD and didn't have any money and seemed to be able to write code, and ended up getting a job with what was then Digital Equipment Corporation, writing software for them. And I got stuck there pretty much ever since, and we went through from digital to compact to HP. And I spent a lot of that time, as was mentioned, travelling the world working with HP's customers, helping them to modernise legacy environments, mostly around the Open VMS side of things, which some of you may know is a legacy operating system that came out of Digital Equipment Corporation originally and now ended up with HP. For the past few years, I've kind of varied that a little bit and spent a lot of time working for the HP Cloud team, mostly as the sort of RabbitMQ guru. Rabbit, of course, is used extensively within OpenStack, which is what HP used for their cloud offering. Around about a year ago, a little over a year ago, I left HP and joined this company, VMS Software Incorporated, which is a kind of a strange sort of startup company based just out of Boston. I'll be up there next week. I'm from New Zealand, by the way, so in addition to the longest title, I possibly had the longest flight, but that's beside the point. And with VMS Software Inc., we've licensed all of that old legacy operating system off of HP, and we have the right to create new versions and things like that. And my role within the company is around open source, figuring out our open source strategy, getting products, open source software onto the platform and promoting that. So how does all this relate to Erlang? Well, my introduction to Erlang probably started around about 2008 timeframe, when I was looking to try and get an AMQP implementation, Advanced Message Queuing Protocol implementation, working on VMS. And I kind of liked the look of RabbitMQ. It had a catchy name and good documentation and things like that, but there was a problem. It was all written in this weird language called Erlang. So, having had a few beers with a friend one day at the airport, this friend basically dared me to try and port Erlang to the Open VMS operating system, which I duly did. So that was kind of my involvement. So, you know, I don't really consider myself a particularly crash-hot Erlang programmer, but I like to think I maybe, as a consequence of doing some of that porting work, actually have a reasonably good understanding of what's going on inside the thing. All completely irrelevant to what we're talking about today, but there you go. Anyway, okay, you read the abstract, you know about me. So, what I'm going to do in the talk is, I've broken it down like this. The introduction and background is really just going to talk about how I came to be involved in doing these Monte Carlo simulations and things like that. How many people here are familiar with Monte Carlo techniques or know anything about them? We've got one or two, so that's good. I'm actually going to do a little bit of an overview. It's very, very high level and fairly simplistic, but just do a little bit of an overview or introduction to Monte Carlo methods, give you some feel for how they're used and what they're all about. Terminology, that's just simple stuff that I'll race through because you all know it. And then just sort of start looking at some of the characteristics that I think make Erlang really good for doing Monte Carlo simulations. Now, one of the things, you know, that you may be thinking is, hey, but a lot of these Monte Carlo simulations tend to be number crunching. Erlang's not necessarily so great at number crunching. But what it is really good at is stringing everything together. So you might have some ports or whatever that are written in C or some other language that are doing all the heavy lifting as far as that number crunching is concerned, and you're using Erlang to string it all together within your SMP environment, within your distributed computing environment, and so forth. So we'll talk a bit about that. I've also kind of got a bit of a random section in there when I was playing around with some ideas here, and I'm still working on some ideas in this space. You know, I realised just how many options there were within Beam for tuning the Erlang VM for multi-core. So I just wanted to talk about some of those briefly. So from a Monte Carlo perspective, this is me many years ago before I had a job and before I had grey hair and things like that, back in 1988, when I embarked upon a PhD in chemical physics, which also had a nice long title, but I didn't come up with that title, my professor did. And we'd kind of managed to score some funding to create a thing called a molecular beam machine, these things were all the rage back in those days for studying chemical reaction dynamics. This is quite a coup for little old New Zealand down the bottom of the world. My professor had managed to get this equipment and we'd put it all together and built this machine to study some of these rather interesting chemical processes. You know, people sort of think, oh yeah, you know, chemicals react, molecules hit each other, reaction happens. You know, you put two things in a test tube and shake it up and there's a colour change or heat evolved or some smelly gas comes out or whatever. But in order for those reactions to occur, the molecules actually have to collide quite often at specific orientations to one another. It's not just any random collision. And what we were looking at studying with this apparatus was those sorts of collision dynamics. How do these things actually have to collide with one another? But there's a problem with these machines. They break down a lot. They're ridiculously complicated. There's lots of wires and lots of pipes and all sorts of fancy bits and pieces. And we would spend a lot of time at the start of my project anyway, designing components and then having to wait for them to be built or components to be shipped from overseas or just general downtime. And as I think I commented here, even when the machine was behaving itself and working, it would actually take several days to get down to an acceptable vacuum before we could do experiments. And my professor really did not like me just sitting around reading the newspaper doing nothing. And I didn't really like doing that much either. So I came up with the idea that, well, while I've got all this dead time with the experiment, why don't I start looking at the theory and figuring out how I can simulate some of this stuff? And in those days, compute resources were fairly lean, as I've said there. We had an old VAX VMS system at the university with 26 megabytes of RAM, serving most of the campus of what was then, I suppose, 6,000 or 8,000 students, obviously not all using the machine at once or anything like that. But we had limited compute resources. And trying to solve some of these molecular dynamics problems via conventional numerical means just wasn't going to happen. It just couldn't be done with the computing resources we had available. And so feeling a little bit depressed about this, I wandered off to the library, which, you know, the older people here will know is a thing that has books in it. And I stumbled across some books on these things called Monte Carlo methods. I thought, okay, well, that sounds pretty cool, so let's get stuck into that. It actually bypassed a lot of these constraints that I was faced in terms of the compute resources. It did have a consequence that calculations would take an awfully long time, but whatever, I could actually kind of see stuff happening and it was working. Nailed the PhD eventually, totally broke, ended up at digital, earned money. Then I got bored around about 2000 and went back to the university again and we did some more research. The machine had evolved considerably since this time and there was a new technique on the horizon for studying chemical reactions which was called ion imaging. And ion imaging was kind of quite cool. If one of the products of your reaction is an ion, you can use electrostatic lenses and so forth to focus that essentially up onto a phosphor and basically take a pile of photos of the thing. And if you gather enough images, you know, you get enough of these things, you can create an average or whatever image or an overall summed up image and that actually gives you some data about where, when those molecules collide, where the reactants are scattering to. And you can use that information to recover a lot of information about the reaction dynamics. But true to form, despite the fact that it had been maybe a decade or 8 years at least since I'd played with the beam machine, true to form, it still broke down and we had to wait for parts and things like that. So I wrote some code. Since I'd been out in the workforce for a few years, I'd learned other languages like C and the evil C++. But we still had relatively limited computing power. We were, however, able to produce much prettier graphs. So I set about simulating again what should happen with this ion imaging technique. We never got images that actually looked quite as good as those ones over there on your left, and they certainly weren't in colour, but the whole experiment did work pretty well, and the simulations were actually very, very useful in terms of guiding the experiment. So this was essentially my introduction to Monte Carlo techniques as a method of simulating physical processes, in this case chemical reactions and things like that. So what are these? Sorry.
The form of RCWA that you use?
Sorry?
You use the form of RCWA?
RCWA?
Correlated analysis?
No. I mean, I could talk about the mathematics of analysing those images and things like that, but it's terribly boring and there's lots of squiggly Greek symbols and things like that. And I've probably forgotten most of it anyway. So putting it really simply, Monte Carlo methods, randomised algorithms, computational experiments, okay? They can be used as approximations where analytical computation is not tractable. And I'll talk a little bit more about the history of Monte Carlo methods very soon. But, you know, where normal numerical methods just aren't feasible, you know, your equations might just have 4 or 5 integral signs and all sorts of nasty variables and things that you need to deal with, and trying to use conventional numerical methods is, for whatever reason, just not feasible. All the rest is sort of more formal words. But, you know, just to take a really trivial example over there in the yellow, so, you know, just to illustrate what I mean by this technique, what's the probability that 10 dice throws are going to add up to exactly 32? Now, you know, we're all reasonably smart people here, you guys more so than me, and I'm sure you could easily calculate the exact solution, not a problem. The Monte Carlo approach is to do an experiment. Let's go and throw 10 dice some large number of times and see how many times they add up to 32. And then divide that by n. And we can work out the probability. Okay? So we've replaced theory essentially with a perfectly valid and, in this case, very, very simple experiment. This ends up being a fairly universal technique for the solution of many mathematical and physical problems. Natural phenomena like the reactions and so forth that I was looking at, simulations of your experimental apparatus, and even just numerical analysis. It can be used as a fairly general technique for solving very complex integrals and things like that. So it has long been recognised as a very useful technique, and over the years it's found application in a broad number of areas. I've listed some of them there. I mentioned integrals before, molecular dynamics, yes, quite popular in the finance industry and things like that. Interestingly enough, you know, whilst you talk about random numbers and probability distributions and things like that, Monte Carlo methods are applicable to both deterministic and probabilistic problems. And what I mean there is probabilistic, well, okay, so there's a probability distribution of your variables or whatever. Deterministic, these are things that can be specified mathematically exactly and involve absolutely no chance whatsoever. Sometimes it's actually possible to restructure those problems in such a way that you can solve them using some probabilistic approach. So you can spin a deterministic problem round into a probabilistic problem and solve it using Monte Carlo methods. The history of Monte Carlo methods, well, it's probably been around since the dawn of time, but probably one of the first documented cases was some French mathematician with a very long and difficult to pronounce name, who obviously had a lot of spare time on his hands, because I tell you, this way of calculating pi is not good. Maybe he just had a whole lot of people doing it at once or something, I really don't know, but you know, I can't imagine that he would have got much past a value of 3 as his approximation for pi using this technique by hand. I won't read it all there, but basically this was one of the first documented examples of what, by today's reckoning, would be a Monte Carlo simulation. Where Monte Carlo methods in their modern form come from is around about 1994, 95, 1945, during the Second World War at Los Alamos, where you had people like John von Neumann and many other famous scientists working on the Manhattan Project, developing the atomic bomb. And they were faced with a large number of mathematically complex problems to solve along the way. One of those was to do with, as I've said there, random neutron diffusion in fissile material. Now, this in part related to actually building the bomb, but also in part related to them not frying themselves. So they were very keen to actually make sure they had things right when it came to some of this data. And John von Neumann can probably be credited mostly with pinning down Monte Carlo techniques and formalising them. And indeed, a lot of the refinements and so forth that he and other mathematicians on the project developed are still in usage today. In those days, as I recall seeing a picture, a lot of the calculations were actually done by a large group of women with these sort of, tappity tap tap, pull the lever and a piece of paper comes out and I'd hand it on to the next person. They didn't have modern day computing facilities. But with the advent of modern day computing facilities, and as computers get more and more powerful, the sorts of problems you can solve by this technique just get bigger and bigger and more interesting. I've also mentioned a couple of other guys, Maxwell and Boltzmann, if you know your chemistry and physics. They've got equations and so forth named after them. They, however, used Monte Carlo methods to solve these problems, but they never really thought about it in those terms. They were more interested in the answers than the techniques. Von Neumann and his colleagues appreciated the value of the techniques. I've talked about this already, where you can spin deterministic problems round into probabilistic ones by replacing theory with experiment whenever you can't use the theory for some reason. Probabilistic is fairly self-explanatory. Observe random values chosen in such a way that they directly simulate the physical process of the original problem. Okay, so you're choosing values with appropriate probability. So for, say, just a trivial thing in some of the work I was doing with the beam machine, the molecules that were flying through the beam machine conform to a certain velocity distribution. That's a probability distribution. So one of the things I was doing, for example, was selecting velocities with appropriate probability for the collisions that I was examining. All of this then, of course, spins round to a need for a good source of random numbers. And random numbers, of course, are essential to any Monte Carlo simulation. You've got to be able to calculate them efficiently. You also do want them to be random. Just a point of note, there's no such thing as a single random number, that is just a number. It has to be a sequence of numbers where there is no, well, it's not a sequence, there's no defined sequence. A set of numbers that have no known correlation. Now, the best we can do on computers is what are referred to as pseudo-random numbers, and they do have a period which is essentially determined by the largest integer that you can represent on the computer in question. But to all extents and purposes, these pseudo-random number generators today are more than adequate for pretty much any Monte Carlo simulation. There are, of course, truly random physical processes, and I've listed some of them there: radioactive decay, thermal noise, cosmic rays. I suppose hypothetically you could, interface a Geiger counter to your computer and put a piece of plutonium beside it, but that really doesn't sound like a good way of generating random numbers to me. When you talk about random numbers, a lot of people think that these are just random numbers distributed uniformly between two values or something like that. There are, of course, many other types of distribution. I mentioned the velocity of molecules flying around in my beam machine, or even flying around in this room. They conform to something that more approximates a Gaussian distribution. And I've just tried to illustrate that here, where there are two noise spectra. The top one is sampled from a uniform distribution, so every value has the same probability. The bottom one is noise sampled from a Gaussian distribution, not the same probability. I mean, obviously the resultant histograms are a little bit rough, but they're definitely not the same shape, right? So what you tend to find is most of those random number generation algorithms that languages like Erlang or C or whatever provide will be uniform, and you will then need to provide some sort of transformation to convert those uniformly distributed random numbers into a probability distribution that is applicable to the problem you're trying to solve. Interesting point here, who knows that, there's this dude called A.K. Erlang who actually has a probability distribution named after him. So this is obviously where the name of the Erlang language comes from. And he was one of the first to start examining things like I've got in the little yellow box down there around interactions of people making calls with operators at switching stations and so forth. But there are many, many non-uniform probability distributions. I've listed a few there. Gaussian would be the most common, I suppose, but I'm sure you're all familiar with the others. And as I say, normally in any of these simulations, you'll use your computer or your language's uniform random number generator, pseudo-random number generator, and you'll apply a transformation to get a value which conforms to the probability distribution that you're working with. One problem that you face with this sort of thing, I mean, you are essentially, with Monte Carlo, you're doing an experiment, and you do it many, many times with many, many different sets of values, and you basically end up taking an average. Now, in order to refine your answer and to improve the accuracy, by some factor of n, you basically need to do n squared more samples, right? So it's computationally intensive as far as improving the accuracy of the calculation is concerned. What people have discovered, and this even dates back to the likes of von Neumann and so forth back in the 1940s, they realised things. I mean, they were smart guys, of course. They realised things like, hey, there are these values out on the wings of these distributions that really contribute nothing to the overall answer. So why waste our time even looking at them? So they came up with that was referred to as importance sampling. Why waste your time looking at things that are completely irrelevant to the final answer? They're just not going to count. So they actually devised a whole lot of techniques which are known as variance reduction techniques that don't distort the problem in any way. They don't introduce some sort of unnecessary bias, but they do allow you to calculate an answer more quickly or potentially get a slightly more accurate answer more quickly. Now, there are books on this stuff, and it goes on and on and on. Anyway. But another way that you can improve accuracy or speed up these calculations is, of course, parallelism. And this is the biggie here where, I'm talking about SMP and things like that, is that most Monte Carlo simulations are easy to parallelize. You could run the same simulation with different random numbers on multiple cores, combine the results, and you've got an answer, okay? So like I say here, say we want to find an estimate around about n times faster, where n is the number of cores or CPUs we've got at our disposal. Yeah. So running these things in parallel, they're very amenable to running in parallel, be that multi-core or distributed. So just very, very quickly, some terminology, just like people need to know it. Concurrency, we all know what concurrency is, we all know what parallel processing is, but just for the sake of it. Concurrency, property of systems in which several computations are executing simultaneously and potentially interacting with one another. Parallel, simultaneous use of one or more CPUs or processors, etc., etc. We won't talk about bottlenecks because nobody likes them. So I mentioned with concurrency there, sometimes there will be interaction. The idea of parallelism, hopefully there is no interaction, although, in theory and practice are often two very different things, and trying to avoid any interaction in either space is just about impossible in many cases. Now here's a picture of Joe doing something really nasty to a cupcake with a soldering iron. I really don't understand, but I thought it was a cool picture. So having defined concurrency and parallelism, I thought, well, how does Erlang define them? Okay, so as Erlang defines them, concurrency refers to having many actors running independently but not necessarily at the same time. It defines parallelism as many actors running at exactly the same time. And I cut and pasted some text out of Wikipedia that kind of made me laugh a little bit, and I suspect that some of the object-oriented programmers might get a little upset with, but that's life. Multiprocessor, multi-core, all standard stuff. Multiprocessor, more than one processor sharing bus and memory. Multi-core, more than one processor on a chip, each with its local memory and access to shared memory. Just so you know. Okay, so with all the formalities out of the way, I thought we'll look at a simple experiment. I mentioned the work that French guy did back in 1777 to estimate pi. And I had a little bit of a search of the net, and I found that this piece of code with the link there, which is a nice little Erlang example of Buffin's needle problem. Okay, it's an Erlang implementation of calculating pi via Monte Carlo means, as I say, written completely in Erlang. And it's kind of, it's obviously a trivial example, but it does illustrate very nicely the ability for this to scale across multiple cores. As far as this program goes, all you need to do is specify the number of Erlang processes and the number of trials that you want to do. It goes away and comes back with an answer. The good thing here is, because this is actually a computationally intensive thing, each of those Erlang processes actually completely obliterates 100% of the core. So if you've got 30 of these processes running, you're basically going to be using up 100% of 30 cores on your system. So I ran some tests on a 64-core server running CentOS with Erlang 17, And I did that for 1 to 60 processes, so essentially chewing up 100% of between 1 and 60 cores on that machine. I also thought, just for comparative purposes, I would do it with 1 to 60 Erlang processes with only 32 cores enabled. And also this particular system supported hyperthreading, so I thought I'd see what effect that might have. Did like 100 million samples in each case, and this is what I was saying, if Buffman and his friends were calculating pi this way, it would have taken them a heck of a long time to do 100 million, and the best answer I got out of this for 100 million was 3.141. Okay. So there was the result. It's basically pretty much as you'd expect. The blue line, which unfortunately is somewhat obscured by the red line, but the blue line is the good line with 1 to 60 processes, all 64 cores available. And it goes pretty much as I'd expect. I mean, basically doubling the number of processes roughly halves the overall time taken to complete the calculation. There's a bit of a glitch around 57 cores, which I think is just some syncing issue. I haven't really looked into it. I wasn't too concerned. I suspect it's actually the operating system as opposed to an Erlang issue. The other two lines, the red and purple lines, show with just 32 cores enabled or with hyperthreading enabled, and you can see things start glitching a bit around about the 32 process mark, which is kind of what you'd expect, but I was pleasantly surprised that the glitching, the going back up, it wasn't as bad as I thought it was going to be. I was kind of actually surprised about that, but I would say mileage might vary in that respect, because this is a totally trivial calculation. If you had a much more complex workload, I dare say that with only 32 cores enabled, once you hit that barrier, you would probably start noticing some serious degradation.
So in this example, hyperthreading
It made virtually no difference. I'll talk about it later on, but I found that mixed results with hyperthreading. Yeah. Just very, very quickly, I mean, when it comes to just how much scalability you can get out, how much speed up you can get with the program, I mean, it all basically comes down to Armdale's law, and it's limited by the serial part of the program. I mean, it's kind of common sense. But as I say, a lot of these Monte Carlo simulations, like obviously the pi calculation is totally trivial, a lot of these simulations are basically trivially parallelizable. There really doesn't need to be any interaction between the threads running on separate cores at all. So more complicated problems. I was intrigued. I'd been reading a paper that was written by Google back in 2013 where they were looking at applying Monte Carlo methods to the solution of certain big data problems. And I thought, well, okay, that's kind of interesting. How can we hook Erlang in with that? And as I say, this is something I'm looking into. No solid results or anything yet. If you look in general terms, though, at the use of Erlang for Monte Carlo calculations, it's fairly limited. A few trivial examples and test programs and things like that. And I think a lot of that does come back to my comment earlier about the fact that, Erlang's it's not a number crunching language. It wasn't designed to be. It wasn't intended to be. But what it is good at is doing the SMP thing, doing the distributed thing, and you can use it as the vehicle for stringing together other code that's written in a language more amenable to doing those calculations. If you look at programs like React, for example, LevelDB, C++ code, Bitcask, C++ code. LevelDB is evil C++ code. It's not pure Erlang, okay? So I think, as I say, where Erlang comes in is acting as the glue, acting as the mechanism to string all this stuff together. But as a general comment, as I say, the use of Monte Carlo for big data analysis type work seems to be growing. And I've cited a few examples there: genome research, marketing research, medical imaging, things like that. It's starting to find application in these areas. And it would be nice if we could string Erlang into the equation here. This is the paper I was referring to that was written by Google back in 2013. And it uses a special Monte Carlo technique based around the use of Bayesian statistics. It's a good paper to read if you're having trouble sleeping. It's pretty good, but it's hard going. It's heavy reading. And it's an interesting technique. I mean, I've kind of been really rude, I think, there and said that basically it boils down to a form of sharding, but it's kind of not too far from the truth. It's an interesting read, as I say, if you feel like getting into that sort of thing. And I'm currently just doing some research looking at what I can do with Erlang and this stuff. The paper itself talks more about distributed as opposed to multi-core, but from an Erlang perspective, doesn't matter. This is just amusement for my sake. This whole big data thing just seems a little bit crazy, so I'll just have a small rant. I also like the fact here that, they're saying by 2018 the United States alone could face a shortage of around 140 to 190,000 people with deep analytical skills and 1.5 million managers. Hang on, the ratio seems wrong to me. But I'm not sure what this was trying to say. It sort of seemed to be saying to me that software engineers these days, all they knew how to do is to write code and they didn't actually understand data. Well, that seems a little bit harsh to me, and I would kind of question it. I just found it rather amusing. Anyway, it's good to know that we'll probably all have jobs, so it's cool. Just going to go off on a little bit of a tangent here and talk about Erlang's approach to SMP and the role of Erlang. Potentially the role of Erlang in these Monte Carlo calculations. Doing SMP by hand is hard. If you have to sit down with a C compiler and write code that runs on multiple cores, deals with all this shared memory threads, locking, all that sort of stuff, you seriously get a headache, and you'll probably soon start developing liver damage as well for other reasons. Even with languages like Java, bless it, threading in Java was a real pain in the butt, as far as I recall. Languages like Scala have helped to address that to some degree, quite nicely, to be fair to Scala. And you've got things like the akka toolkit to help you with the construction of distributed and concurrent applications. But it's nowhere near as transparent as it is with Erlang. You sit down, you write a piece of Erlang code, you barely even have to think about SMP or whatever. It's there. Magic happens. Similarly, when I was doing my PhD, there were these APIs, PVM and MPI were kind of available, and very good pieces of code that would allow you to distribute applications across generally across multiple machines. But once again, there's specialist knowledge required. You need to understand those APIs. You need specific knowledge on how to incorporate that into your C code or whatever. In contrast, Erlang, magic happens, In general, it's transparent to the programmer that there's all this stuff going on around SMP. It's got all the good bits you need in there to avoid all those headaches around, coordinating access to shared memory. It doesn't even let you do it. It's, got all the asynchronous message passing, distribution transparency, all that stuff that most other languages, you'll have to craft something. I mean, I've seen a disturbing number of, in my travels over the years, I've seen a disturbingly large volume of code that does all this sort of stuff. And these are applications that might have been in use for 20 or so years, written in languages like Pascal and things like that. And when they break in a major way, and it's a nightmare to try and figure out what the heck happened. Erlang does so much good stuff for you, it's a blessing. I would, however, say that, obviously, the Erlang virtual machine, Beam, is written in C, and it's a pretty hairy piece of C code. But you don't have to worry about that. It's taking care of all this good stuff for you. Okay, so I commented before that, Erlang's not such a great language for number crunching. It's not. That's not what Erlang was designed for in the first place. You might be able to get a little bit more using something like Hype in some situations for some sort of number crunching type application. It was interesting hearing the guys talk yesterday about how they're looking to use the LLVM compiler project. So maybe Erlang will get to the point of being just-in-time compiled, much like some of the JVM-based languages or something like that. I don't know. There's certainly a lot of work going on in that space. Point I made, and it's something that Garrett Smith did a good talk about in Chicago back in 2014, is that calculations not conducive to Erlang can be offloaded and implemented in a port or something like that, or a driver that you would write in C, C++. So I mentioned Bitcask and LevelDB as being a couple of good examples of something like that. Heterogeneous applications are the norm. Homogeneous applications, not really the norm. It's a fact of life, I think. Obviously, if you're going to start spinning off ports like this, you need to be very careful to make sure that they operate in an asynchronous manner. Otherwise, you'll end up blocking schedulers and bad things will happen and you'll end up essentially synchronizing all your code. But interesting talk from Garrett, as I say, back in 2014, and he's got a little bit of code up there on GitHub, some of the ideas that he was playing with around this approach of having Erlang basically coordinating the whole thing, but you may have other applications in the mix, these ports or drivers that are implemented in 3GL code. Just very quickly, I thought I'd put up a comparison with Scala for dealing with SMP. As I say, it's not transparent. It's got some nice stuff in there, but it's not totally transparent. Let's say we've got a really simple example here. We've got some tail recursive method called doIt, which is going to do some number of trials. What's that number? 100 million or something like that, trials, and return an answer. We can parallelize that really simply, as I've shown here. Basically, is parallelize a map over a collection. So we're going to do 16 separate computations, bit of a map, bit of a reduce, got our answer. That's quite neat, not too hard to change. If we then want to make that take advantage of multiple cores, again, very simple. We just drop in the .par method and it converts it to running in parallel. But it's not transparent and it's not distributed. It's multi-core. So Scala's got some really good stuff in for this kind of thing, but it's still not as nice, I think, as the Erlang approach. To be fair, though, I do quite like some of these languages. I quite like Rust. It's obviously still got a way to go. And all of these languages that I've listed there, I think, have their virtues. And as usual, it's a case of using the right tool for the right job. What is really good to see, though, is that I think there's now general appreciation of the value of some of these functional languages like Erlang, Rust, and so forth, when it comes to implementing these massively scalable and fault-tolerant, highly concurrent applications. Okay, it's really good to see. So, just very quickly, just talk about a few things. I mean, most of you, I'm sure, are familiar with tuning the VM for this sort of thing. And you'll know that by default, when you run beam or when you run the Erl command, beam will try and figure out, Erl will try and figure out whether you're on a system with one or more cores, and it will start either beam or beam.smp accordingly. You can obviously override that using the -SMP enable disable flag. By default, it takes the auto approach. And it will basically try and use whatever cores are available to be used. It will start up a scheduler thread for each, and those schedulers have their own little run queues, which, as I say there, are a list of Erlang processes on which the thread is going to spend a slice of time. And Erlang's got some quite nifty code with these schedulers where if a scheduler has too many tasks or whatever, Erlang, the VM, can try and balance the load across the available schedulers. This was introduced, I can't remember, must have been around 13, maybe a little later. Anyway, so the +S option is used to specify a number of scheduler threads, and as I say, unless instructed otherwise, it's going to try and spin up, the VM is going to try and spin up as many, it's going to try and determine how many cores are available and can be used, and it's going to spin up that number of scheduler threads. If it can't make any determination, it's going to default to 1, which might be a bad thing and slow down your application. So hopefully on whatever platform you're using Erlang, it can figure out what your CPU topology looks like. Now, +S is, the simple option. There are a whole range of other flags that you can use to tune scheduler threads, and I just wanted to go through just a couple of them really. Scheduler wake-up intervals are an interesting one that started off life actually as a bit of an experiment, and if you read the documentation, it kind of looks like it may disappear at some stage. So this option, SFWI, when a scheduler thread runs out of stuff to do, it will fall asleep. Waking it up, again, requires a system call. System calls take time. So this flag was built in, included to try and limit the impact of this kind of thing happening. As I say, I'm not sure. It may go away, it may not. But, generally speaking, you want to try and keep all those scheduler threads doing something and try and avoid them from going to sleep, because if they go to sleep, it takes time to wake them up. Much like getting my son out of bed in the morning is just about impossible. That's kind of more than a system call. That's a beating around the head. I mentioned before how the schedulers have a run queue and so forth, and Erlang will try and the VM will try and balance the workload. There are two approaches to that. One is what's called compaction of load, where the VM will attempt to fully load as many scheduler threads as possible. The issue you potentially have there is that you may end up with some scheduler threads with absolutely nothing to do and they will fall asleep. I should, however, note that compaction of load is the default scheduling model. The other model is utilization balancing of load, where basically the VM will try and balance the workload across all threads, all scheduler threads. 5 minutes to go? Okay, that'll be right. And you can tune that, and that's something to watch out for if you have applications in this space. So in general, if you have an SMP application, you've got performance issues, there are a lot of knobs you can play with, but chances are what's optimal for your configuration may not be optimal for another application, so you need to play around and experiment. In general, bind your schedulers to cores. That can have a big performance improvement. Turn off load compacting. Don't let your schedulers sleep. Bad stuff will happen. You could have that issue. I mean, these are things you would need to watch out for, of course. Yeah, if you're locking scheduler threads to a core and you then start up another instance of Beam and you do likewise, you're probably going to shoot yourself in the foot somewhere, right? Just very, very quickly then, some CPU topology examples. You can do Erlang system info CPU topology and it will tell you good stuff. Like in this case, this is my laptop. It's a single dual-core processor, so one processor, 2 cores. It's got hyperthreading enabled, which are the logical things you can see out there. A somewhat bigger example, 8-core processor with hyperthreading. Again, the same deal. Just 2 CPUs, 8 cores on each, and hyperthreading enabled. I won't go through this because we'll run out of time, but basically this just illustrates when you start up, by default, schedulers are not bound to cores, okay? You can use the SBT option to specify various ways in which they get bound to cores, and it's generally quite a good idea to do that binding in one way or another, but read the documentation as to which option is best potentially for you. We talked about hyperthreading. As I say, I've had mixed results. I mean, give it a spin, see if it works for you. It's potentially useful. As I say, I've just had some things where it seems to make no difference. In other cases, it's worked quite well. Okay, so very quickly, summary and conclusions. Erlang has many traits that make it ideal for multi-core and certain types of problems. Problems that conform to naturally concurrent patterns, and that includes many problems that can be many sorts of Monte Carlo type simulations which are trivially parallelizable. You can run those problems on multiple cores using different sets of values and merge the results very, very easily. Monte Carlo calculations generally involve number crunching. Erlang's not very good at that. You can spin that out to a port written in another language that will do the job better, and use Erlang to string the program together and act as the glue that coordinates all the activities. Okay. We'll just finish up with a quote from Joe, this time without him toasting a cupcake, and just taken from his book, which I think is poignant and relevant to the whole concurrency thing. Okay, and then finally, any questions and a nice picture? Yeah. That's actually a very good question. The question, for those who didn't hear it, how to approach parallelizing the pseudo-random number generation. I knew somebody would ask me that, and it is always a problem. So yeah, it is actually. And if you look, for example, I don't have a particularly good answer for you at the moment, but it's interesting to see how, if you look over the years, how Java seems to come up with some new pseudo-random number generator just about every release, right? It's an ongoing issue, and that can be the real killer. Yeah, very good question. Sorry, glossed over it. Yeah. Mm.
The other stuff is on TinyMD, you can pre-calculate the massive number of different generation parameters, which have a mathematical improvement to generate totally independent signals, which will never overlap with each other. I've already computed about 200 million keys, 200 million pairs of the generation parameter using Tokyo University's supercomputer system as well. And it's on GitHub, although it'll take time on downloading 40 or 50 gigabytes of data from that. But anyway, you have the key, and you have the algorithm. It's ready on the TinyMD implementation of mine.
Thank you.
Your presentation is absolutely intriguing, and I just made the comment that it's already on the it's ready.
Excellent. Alrighty, any more questions? Okay, tea and coffee. Thank you.